Okay, so I guess that's pretty much everyone back. So if we progress on to the joints. And so what we're going to be looking at now is how you get this interface between the bones, which clearly have functional advantage, and that we find a way of connecting those bones together to ensure that we have two functions that are achieved. So we're looking at a union of two or maybe more bones. And every joint has to provide an element of mobility or motion and an element of stability as well. There are instances where stability is the overriding function that's achieved from the joint. There are instances where motion is the more obvious of the two functions that are achieved. However, they tend to be competing. If you have lots of stability, that means inherently you have very little mobility, and vice versa. But there are conditions that we'll describe again, predominantly osteoarthritis, that overrides these two main functions and requires then the joint to be replaced. So there's an order of how joints work. We can have a fibrous joint, a cartilaginous joint, or a synovial joint is one way of dividing up types of joints or classifying joints. The synovial joint is the one that we've been discussing yesterday, looking at hips, shoulders, knees, and so on. And they're the obvious joints. They're the ones that give us predominantly movement. Cartilaginous joint, that's the joint that holds the two bones of the pelvis together. There is more stability here, so we haven't got the ability to move one side of our pelvis relative to another. So there's greater stability. As a consequence, there's less mobility. Going to the other extreme, where there's lots of stability and pretty much no mobility, is within the skull. And our skull is derived or is made from a number of separate bones, and they're effectively fused together by these fibrous joints. And so an ability to classify joints in some way, shape, or form is quite helpful, and this is based on the structure. We could then choose to look at the types of movement that you can get. So typically within a synovial joint, but not exclusively, you can also classify joints based on the type of movement that's achieved. Be that in one axis, be that in two axis, or be that multi-axial. So we discussed yesterday about the knee joint, the TF joint as we described it in the notes yesterday, where it has predominantly flexion extension, so the obvious bending of the knee that one would expect, but also some abduction, adduction, where the knee moves away and towards the midline, and also internal and external rotation. And so the knee is an example, a subtle example of a multi-axial joint. We could look at the gross movements that were permitted, or we could look at the geometry of the articulating surfaces. So there are various different ways in which we can describe a joint. Depends very much on what you're trying to achieve with your description as to which of these classifications you may adopt. If you're trying to highlight the benefits of a uniaxial versus a biaxial joint, for example, then you would adopt the classification at the top. But from a biomechanical perspective, again, with our origins derived from mechanical engineering, probably the most interesting and the most focused on joint is the synovial joint. And that's the joint that features at the bottom of our stability rating, but at the top of our mobility rating. And so very much consistent with what a mechanical engineer would expect to be doing. Not necessarily worried about having something built such that it doesn't move, but having mobility as a key function of their work. And so a synovial joint encapsulates quite literally just that, where we have an ability of one surface to move relative to another. And again, we touched on this yesterday. This is a a crude schematic of the knee joint that we'll explore in more detail in a second. But there are a series of features of a synovial joint, one of which is the articular cartilage. So that's the purple covering of both of the bones. And so we have a thin layer of cartilage on the tibia. And we have a thin layer of cartilage on the femur. And so the cartilage is, again, trying to draw a comparison to examples that we may have seen previously with a chicken bone. If you were to pull the end of a chicken bone, or the kind of the fibrous bit on top of a chicken bone off, then you would see a shiny white surface underneath. And what you've done, if you were to kind of snap the two weak parts of a bone in two, is you've probably dislocated this joint, and you've revealed this shiny white surface underneath. That's the articular cartilage, and it's that causes biomechanical engineers so much interest in a method or with reason of trying to replicate its function. So we have then this layer that surrounds it all. And this is quite difficult to imagine extrapolating from 2D to 3D, because that wraps all the way around the joint. And it's that capsule and the synovial membrane it's that watertight capsule it creates that's important, because within it we then have our synovial fluid. So we have a capsule that's created by the membrane. And we have a very small volume of synovial fluid that's within that as well. Whilst this is a 2D cut through the knee, we need to be aware that somewhere within the knee are two ligaments that are crossing over, are cruciate ligaments, if I can spell them. And then on the outside of the knee as well, medially and laterally, are the collateral ligaments too. So the knee joint is, even then, still relatively simple in terms of construction. It's not a huge innovation from what engineers are used to when it comes to any kind of bearing. You have two surfaces that slide past one another. You have the fluid, some kind of grease within it, and then you make sure that you encapsulate it all so that no debris can get in. And so the human body and engineering have perhaps come by coincidence, or maybe unsurprisingly, to a very similar solution to a very similar problem. And so this just describes the membrane that's created around the joint. And on the inside of the synovial membrane, we have cells that produce synovial fluid. And as we discussed yesterday, the synovium, those layers of cells that produce synovial fluid, are important to maintain the health of the joint. And without wanting to repeat all of yesterday, all of this lot, when it works well, can last for 70 years plus. And there's significance in that because it highlights how efficient the joint is versus what the collective wisdom of man can produce, having attempted a similar solution for the best part of, well, probably ironically about 70 years now. There's a little picture on the bottom which describes a schematic of a cut through of articular cartilage. So articular cartilage is key to the effectiveness of this joint. It increases the area of load distribution. So it's not a solid material. It's an elastic material that undergoes deformation to ensure that we don't just have a very small point of contact. Were this articular cartilage not there, then our load would be distributed through a very small area, and so obviously the stress would be far greater. It also is, going back to any occasion that we've seen synovial fluid, very shiny and very smooth. And again, they're two key traits of any engineering surface that you're trying to design that is intended to withstand wear and to minimize wear. And so they're two key traits that really add significantly to the function. Bizarrely, perhaps, it's created from material that's very similar to bone. So you have visual appearances that are quite different, quite stark, functional differences that again are quite dramatically changed, but we have a material composition that is not hugely dissimilar to the bone. We have an extracellular matrix, and we have fibers within that extracellular matrix, and we have proteins and cells. And again, because of this solid fluid composition, we end up in a position where we have viscoelasticity within the material too. That just adds complexity to when it comes to trying to understand how this material works. It's not a linear elastic material. There is viscoelasticity within the material too. In part contributed to by the long protein molecules that you see within that little schematic. So we know it's a highly complex material. We know that it has this lifespan of 70 years versus other solutions that are far inferior to it. But it still goes wrong. It still starts to fail over time. As soon as we get any kind of failure of the tissue, then the degradation almost increases beyond recognition. You can have a healthy joint, and then as soon as you start getting disruption, that disruption causes more disruption, and the process becomes very quickly accelerated. Osteoarthritis is key. It's not really driven by a mechanical condition. It's driven predominantly by proteins, but then as soon as you start getting wear, that wear increases excessively. A greater risk for younger patients is a focal defect, a small area of damage of the tissue. The two are, I guess, similar in terms of their outcome, and that is that you have damage to the surface. But in terms of the approach that you would use to repair both of them, that's very different. Where you have osteoarthritis, which is affecting chronically the entire surface, or maybe even more than one joint, there is no real solution apart from to replace it at some point. And given the lifespan, the limited lifespan of replacements of 15, 20 years, you want to put off that process as long as possible. So instead, what you can do is add chemicals into the joint, hyaluronic acid, for example, which is the lubricating component of the joint, to try and mitigate the pain of the joint itself. And so where you have disruption of this smooth surface, you end up exposing the underlying bone, and that's very sensitive to any kind of loading. So the articular cartilage itself doesn't have much innovation. There's relatively little sensing in the articular cartilage. Take the articular cartilage away and expose the bone, and people feel that as pain. And so if big regions of the articular cartilage start to degrade, start to wear away, to lead to osteoarthritis, then there's little that can be done aside from taking the whole joint out and replacing it. If you just have a small area of pain, damage, perhaps caused by a sporting injury or something that happened and has happened once only, then there are tissue engineering solutions that are trying to look at using cells to repair it. And so cartilage itself is a material almost the opposite of bone in terms of its ability to self-repair. It doesn't repair well at all. And so where you have damage such as that, it's not a matter of wrapping the joint up in plaster and keeping it still and knowing that the articular cartilage would repair itself. When there is a small area of damage, then there are tissue-based or cell-based solutions that scientists are working on to try and fix those focal defects. And so they grow up tissue or cells, they'd inject it within the defect, and then they would cover that back over again and hope those cells will grow back into articular cartilage. But that treatment currently is only successful in areas of very focused damage. So where you have a small area of articular cartilage damage in a relatively young patient, that can be attempted to be fixed by tissue-based interventions. However, where there is greater damage to a greater proportion of the surface, that would be requiring ultimately a joint replacement. So here we've got our femoral head that's effectively been pulled out of the pelvis. And we see there's a ligament that's actually securing it in place. And so the pelvis and the hip don't sit together without any constraint at all. There is a ligament that's attaching the inner surface of the pelvis to the femoral head itself. We talked yesterday about the synovial fluid, and there are different ways of considering synovial fluid. The string test is one that we said yesterday, whereby if the synovial fluid extends between your forefinger and your thumb, then that indicates that you've got healthy fluid. We should be seeing nice, clear liquid fluid within the joint. If you get to cloudy fluid, then that's an indication of joint disease, perhaps arthritis. And there's very little fluid within the joint itself. Don't be misguided by the size of schematics such as this, thinking that there's a huge reservoir of fluid within the joint. There's very little fluid, less than a mil. Here it's quite interesting. So anyone who's done any mechanical design would appreciate quite how smooth these surfaces are. So the surface of an adult cartilage is about 2.7 microns in terms of roughness. To give you an appreciation as to what happens as the joint degrades with osteoarthritis, that roughness pretty much doubles. And so we have a function of the synovial fluid, and again, it's viscoelastic, or the joint rather is viscoelastic, where you have this fluid and solid structures combining. But a healthy joint enables the body to transmit up to 6 times body weight, at times even more, without it damaging at all. But if we consider these values, so we're looking at 1 to 2.7 microns in terms of roughness. And engineers have focused on those values because, as we keep referring back to, the healthy joint can withstand lots and lots of load, 6 times, 7 times body weight, and withstands up to 70 years of that activity. And yet, when we try and replicate it, despite the fact we know a lot of the fundamental details about the joint, including the roughness, we still can't fabricate a joint that lasts anywhere near that time. And that's fundamentally a problem. When you look at the number of hip and knee replacements that are carried out worldwide, there's 900,000 in the UK carried out alone. Clearly multiply that up considerably for the US and further afield too. And so there's significant interest in the biomechanical field to better understand how the joint works, to better enable us to try and replicate it. And indeed, there's a field of biotribology, tribology being the mechanical study of lubrication and friction and wear, biotribology being effectively those principles applied to the human body. And so tribology is, as defined there by, if you want a credible source, there you are, the Free Dictionary, the science of the mechanisms of friction and lubrication and wear interacting with surfaces that are interacting in relative motion. And the concept of friction is probably something that we tackled in our early school days. You end up trying to calculate the frictional force required to slide one surface over another. And so again, the principles we're talking about are fairly elementary. We're talking about a surface that we understand well, we're talking about a fluid that we understand well, and we're talking about mechanical principles that we understand well. And so again, combining the whole lot together to make a significant advancement in how the technology works shouldn't seem that challenging, but clearly something's happening within the human body that is outside of our current understanding because we just cannot get anywhere close to mimicking it. But understanding this enables us to look at joint technologies in more detail. So whilst we talk about surface roughness, it's important to differentiate between a rough surface and a wavy surface. And so we have a wavy surface, we have a rough surface, and we have a wavy and rough surface. And so we recognize that the articular cartilage has waves in it, but it's really the roughness that we're interested in. And there are various different techniques of measuring roughness. One of the problems with articular cartilage is that it's an elastic material. And again, because this is a mechanical engineering derived science and technology, and you don't get many elastic materials in mechanical engineering, a lot of the technologies for measuring surface roughness require a probe to be in contact with the surface. And so if you have your metal or your ceramic, you can have your probe dragged along the surface and it measures the surface roughness. If you have our elastic or viscoelastic structures such as articular cartilage, if you try and measure the surface roughness of articular cartilage by dragging a probe through it, then you're not going to get an accurate representation of the surface profile itself. You're going to have the probe effectively plowing through the soft tissue and making a groove within it. And so some of these technologies are very limited in terms of their application to our field. And so even fundamentally something as straightforward as quantifying healthy cartilage is actually more demanding than one would perhaps first think. Of course, not only are you trying to seek a technology that allows you to do it, you're trying to get into a circumstance where you can actually get access to healthy articular cartilage, and that can be very challenging. You can't pull open your own joint to measure it, and you won't find many volunteers that are prepared to sacrifice their own joint either. If you go to a hospital, then they're not going to take healthy joints out of the body. They're going to take articular cartilage that is degraded out the body, but you're not getting a measure of healthy joints and a healthy surface. And so if you're a mechanical engineer and you want a number of a bit of material, you would go down to the storeroom, you would get that material, you would take it to the lab, and you would measure it. And that happens routinely, certainly in our department and no doubt elsewhere. But fundamentally, for a biomechanical engineer to do the same thing is almost impossible. I wouldn't know how to begin trying to get hold of some healthy articular cartilage, and then trying to get that anywhere near one of our machines. And then, of course, it has to be a non-contact probe that is able to withstand the reflectiveness of the surface. And so even very simple tasks become far more complicated than they should be. You could take an impression of the articular cartilage surface. So you could put some kind of mold or some kind of paste material and take the inverse of your cartilage surface and measure the roughness of that. We've tried that previously. But the cartilage dries out because of the need for the paste to absorb and to dry out itself. And so you end up with the impression of a dried articular cartilage surface and not the moist articular cartilage surface. And so fundamentally, just doing something as straightforward as quantifying the healthy surface becomes quite challenging. And it's quite challenging because of its structure and because of its ability to deform. And it's this deformation which is key to its functionality. As we said, if we look at the little picture on the right, if we weren't to have deformation in the articular cartilage, we would have the same load going through a far smaller contact area, and so our contact stress would go up. Where we have greater contact stress, then we have greater risk of failure. But if we get back to the fundamentals of kind of high school mechanics, trying to appreciate quite how the joint works. And we can consider various examples, our joints being, or the articular cartilage being highlighted in red, and our synovial fluid in yellow. And again, bearing in mind the very small quantity of synovial fluid that's in the joint, then we need to recognize that these are over-representations or extreme cases of what actually happens. We can measure the frictional coefficient by dividing the amount of force it takes to slide something laterally with the amount of load, or the reaction force from the ground. And if we were to try and push a stone along the ground, then the ratio between the weight of the stone and the amount of force we require, 0.75. So you need a relatively large amount of force to push a stone of a given mass. If we did a similar thing but with steel on ice, then we would need 1/100th of the mass to push it along. And that's not dissimilar to a bearing. So a bearing has a coefficient of friction of about 0.1. However, a synovial joint has a coefficient of friction of about half that again. So whereas we need 1/100th of the weight of the piece of steel to slide it along in terms of the force, we only need 1/200th within a synovial joint. So we've got a system that is twice as effective as the standard conventional bearings that we can manufacture. But lubrication depends on a number of factors. This is called the Stribeck curve, S-T-R-I-B-E-C-K. And it's kind of a theory that's well recognized within mechanical engineering. Across the bottom, we've got the viscosity of our lubricant. We've got our velocity of the contact. And we have that parameter divided by the load that's experienced within the contact. And this yellow plot gives us the relationship between these variables and the frictional coefficient, the coefficient of friction. So if we keep the velocity and the load the same, but we just change the viscosity, then we would see this trend. And that's to say that with no viscosity at all, i.e. Infinitely small viscosity, or imagine that to be none, then we'd have a dry contact, and we'd have a very high coefficient of friction. So any interaction without a lubricant, without any viscosity at all, has a very high frictional coefficient. If you add in a viscosity of a material, or of a lubricant that's very low, then we have a relatively unchanged frictional coefficient, irrespective of how that viscosity increases up to a point. So what that means is that we have over here two surfaces that are quite rough, that are in contact with one another, and we put in a very runny, a very thin, or very low viscosity fluid, and it doesn't change that interaction at all. So we keep this interaction as sliding, going at the same speed, the same load. But in essence, the two rough surfaces, the two surfaces that appear rough here, but the two surfaces continue to rub past one another. if we continue to increase the viscosity of our lubricant, there comes a point when it actually starts to separate the two surfaces out. So you're not increasing the quantity of lubricant, you're increasing the thickness or the viscosity of the lubricant. And it gets to a point where the upper surface and the lower surface are actually marginally separated from one another. Meaning perhaps only the extreme asperities, the extreme rough points of those surfaces are in contact with one another. And so here we see contact between maybe 20–25% of the two surfaces as they slide past. Increase our viscosity, and we can reduce the contact to maybe 10%. Increase the viscosity again, and we get potentially to an area that is fully separated, so that we have no contact at all between the two surfaces. And in essence, the frictional coefficient remains pretty much flat, but the key thing is it remains the lowest of all. So one way of getting to this situation here, which is the optimal situation, because where the surfaces are flowing past one another without contact, we could increase our lubricant viscosity. We could increase the viscosity of our synovial fluid. And people have tried that. People have tried to inject in hyaluronic acid, the lubricating component of this, to effectively increase the proportion of lubricant to other parameters within the fluid. A trouble here is that the cells within the synovial membrane serve to regulate the composition of the fluid. And so if you inject more hyaluronic acid in, then the cells on the inside of this membrane will regulate it to get the concentration back to what it should be. And so altering the synovial fluid viscosity, adding in additional lubricants, has some short-term benefit because you're getting nearer towards this. No one knows quite how close we're getting nearer towards that. But ultimately, the ability of the synovial membrane to regulate the conditions within that joint means that any benefits from increasing this viscosity are short-lived. And so you do get injections into the synovial joint that are trying to drive the joint towards this scenario more often than not. And we need to remember that in the healthy joint, these surfaces are a lot smoother. And so in the healthy joint, we haven't got this extreme case. There's no need to interfere with it because it is quite effective at regulating itself. But when the surfaces become rougher, then you're tending towards inferior lubrication, and so the ability to increase the viscosity is advantageous. That said, however, that's not something that would routinely happen unless the joint degraded in the quality of the articular cartilage. That's right. So here we've got no contact between the two surfaces at all. And your question is, if there's no contact, then how can you have any friction at all? You still have some inherent resistance from the material itself. And so if you've got a very sticky fluid between the two, because it must be sticky because you've increased the viscosity, then you're going to get some inherent resistance as you try and slide one past the other because of the stickiness of the fluid. But the key thing is, and this is a bit of an exaggeration how it goes back up again, it should really remain a bit flatter. But the key thing is that the friction is a lot lower than any of these two scenarios here. You do still get some degradation of the surface because of the thickness or the stickiness of the fluid that slides past them. But in reality, the resistance you get in this picture here, as you correctly say, is very, very much reduced from the other two. There's still a little bit, but by no means the same as the rest. So if we maintain the same viscosity, that's something that is desirable to do. We then look at how our own parameters, things that we can control, can affect the health of our own joints. So if we were to consider just the velocity, so that's to say that as our joint velocity increases, it actually influences the friction within our joints. And so if we were always to have a relatively fast sliding of our knee joint, femoral head and tibial condyles, for example, then we should be in a position where we can encourage the best possible lubrication. So that's to say, perhaps that if we were to run and constantly run everywhere, then we would have the ability to generate this type of condition. The problem, however, is that if we start combining this theory and this theory with our gait analysis from yesterday, yes, you can run, and yes, you can have the leg swing faster, but at some point you come to full extension, and then you have to flex again. So you run, you put your leg down, you're at full extension, and then you have to flex again to swing through. And so doing something quickly, like running, doesn't mean that you're always at faster speeds in your joint. You have times when your joint is at a faster speed, but inevitably you come to a point of full extension where there is zero relative motion, and then you have to flex again. And so at some point, you're always going to have a contact velocity that comes back to zero, because you're at full extension, you stop, and then you flex again. So whilst running means that you move faster, you still have this trend of going from zero to a velocity somewhere, and then stop and go back again. And so there's not much we can do really to influence our velocity, because it's always got to stop, and then it can return to whatever speed that you originally managed to achieve. So we as a person can't really control the viscosity of our fluid, of our synovial fluids. We can't really do much to control the velocity, because at some point we always need to reach full extension and go back again. And so it then comes to load. And we need to be wary of this being the number at which this is divided across. And so as our load increases, we actually go the other way. So decreasing load moves to the right. So if we want to achieve these optimal conditions, we need to have minimal load through the joint that we possibly can. Now, of course, if we start running, then all we do is increase the body load, or the relative body weight that goes through our joints. And so increasing our velocity by something like running is actually in contradiction to what we want to do here. We want to have minimal load through our body. So that's where weight becomes an issue too. You can control your overall body weight, of course, by being careful with your diet. And so the lighter people are likely to have conditions, biomechanical conditions, that are tending towards more optimal joint conditions. But as soon as you start running, where the contact loads increase, then you're perhaps at risk of moving away from here, back to mixed, or indeed back to boundary lubrication. And indeed, engineers have looked at all these parameters. They've looked at the type of coefficient of friction that the human body gets, and it's kind of notionally about here-ish on this graph. So it could be that we're somewhere here, or it could be that we're somewhere kind of here-ish. They've seen that it lasts 70 years, so outside of the realms of anything else. And so reasonably, you'd expect it to be in the kind of hydrodynamic lubrication, which you can't see because that circle's on the top of it, hydrodynamic lubrication. So that is where you have a full layer of fluid that separates the two surfaces. So here's our friction. We draw along until we find the conditions on our plot that meet it best. So it's either there or there. This mixed lubrication just doesn't seem theoretically good enough to give us 70 years of life. And so quite reasonably, people think that we're somewhere here on the plot. However, when you look at the velocity and the loads and the viscosity of our fluid, so if we had a plot on the x-axis, we're here somewhere. So that's where our synovial joint lies, which is totally at odds with the trend. So the parameters of the human joint put us about here somewhere, which causes problems. And we'll come to those problems later on in terms of trying to understand how this material how our interaction can be described. We can't really describe it as boundary lubrication because that scenario wouldn't give us the longevity of the joint that we know exists. And indeed, doesn't really fall on the boundary condition plot. Mixed lubrication, same problem again. Hydrodynamic lubrication, we're not getting the speeds, anywhere near the speeds that we require to achieve a fluid film consistently between the two surfaces. And so this is one of the reasons why our ability to replace the joint is still so poor, because we still cannot understand quite how the natural joint works well. We know that the viscosity of the synovial fluid changes with rate, i.e. that it gets thinner as it gets faster, as you increase the shear rate. The reality is that it's not hugely applicable for the joint because you've got a relatively narrow velocity range in which it works. So the hyaluronic acid is the key element of viscosity and lubrication within the synovial fluid. And so in essence, if you can increase the hyaluronic concentration within the joint, you increase its viscosity. So much like we said earlier on, if you inject hyaluronic acid into the synovial capsule, you can increase the viscosity of the synovial fluid, but only to a point, because the body is very good at taking out materials that shouldn't be there. So it recognizes that the viscosity has been artificially inflated and will gradually reduce that back to the viscosity that it nominally should be. And one of the good things about hyaluronic acid, it's quite attracted to cartilage, and so it sticks to the surface. And so when people are trying to determine the type of lubrication that's being seen here, the fact that the lubricant is known to stick to the surface gives rise to people coming up with new theories that might explain this. And Sir John Charnley was one of the pioneers of joint replacement. He was a surgeon that at times worked with a colleague of mine to try and determine how you can put the natural trends of the body together with engineering theory to come up with more effective joint designs. And it would be important to recognize that from their early work, where there was no solution to replacement at all, to now is a significant leap forward. However, we're still a number of years short of where we want to be. And for this afternoon, we're going to try and explore some of the theories that have been proposed as to how the joint is as well lubricated as it is. Any questions based on that? So articular cartilage is, so whereas bones remodel every 7 years, so your skeleton effectively replaces itself every 7 years, cartilage is far, far slower. And that's one of the problems. So whereas you have osteoarthritis, which is the degradation of those cells, the rate of repair is less than the rate of degradation. Hence why you end up in a position where the articular cartilage becomes non-functioning. It doesn't cover the bone at all. And so you're in a position where, rather than having these two smooth surfaces with no nerves in them at all, we remove these surfaces and you have the underlying bone contacting bone instead. Okay, yeah, so the biology is for others can more authoritatively comment on the biology than me, but I think the key thing for engineers is that if you have a small site of damage within the cartilage, and that can be repaired by biological-based solutions. And they're proving quite successful. And that is to inject in cells that are effectively functioning to grow. And so the ability to regrow small areas of cartilage, or to assist the body in regrowing small areas of cartilage, is doable. That can be achieved. The body can't achieve that on its own. So if we inject in cells, then the body can assist itself in repairing small areas of damage, and that's useful for sports injuries and so on. Where you get larger areas of damage, where the cells are naturally turning themselves off anyway, then if you're to inject more cells, then because the cells are effectively working to degrade themselves, the addition of new cells doesn't really help that process at all. And so, yeah, whereby in younger patients, and so in younger patients where the joint is healthy other than an area of damage that has been caused by some event, the characteristics or the nature of the joint will help repair itself. Where the joint is beginning to degrade anyway as a consequence of cartilage, then there is little benefit in injecting more cells in, because the overall direction of the joint health anyway is to degrade. And so there's limited value that can be achieved by adding in new cells. Nothing to replace it with, but because there's not really a need to ever replace the fluid, because the synovium will continue to produce synovial fluid. But there are, I guess, additions, so that there are fluids that you can add into the joint. For example, hyaluronic acid that you would inject into the joint that would increase the viscosity. So there's nothing really that needs to ever be used to replace synovial fluid, because if you were to put something else in, the body would quickly down-regulate that and take it back out again. And so it's important that you keep the synovium intact, but the ability to temporarily increase the viscosity is achieved by the addition of some viscosupplementation agents. So we effectively are trying to supplement the viscosity of the synovial fluid by adding in some more hyaluronic acid, which is within the fluid anyway. So you're effectively trying to increase the proportion of the viscous component within the synovial fluid to then encourage those more optimal lubricating conditions. So the synovium will remain intact, and so there would be no real need to add anything in to replace the role of the synovial fluid. That would remain as is, and so that the knee joint will be finished off, and the synovium will continue to lubricate that joint. Okay. Great stuff. We'll continue at 2 o'clock or thereabouts.